kinetic energy, sometimes called energy of motion. Things that have motion have kinetic energy. And the amount of energy is equal to 1/2 times the mass times the velocity squared. So for example, if I throw a ball that has a mass of 1 kilogram and it's traveling 4 meters per second, 1/2 times the mass times the velocity squared gives me 8 joules is the units that we use for energy. And you can see here it is the same thing, or it is the name we give to the unit of kilogram meter squared per second squared. If you accelerate an object to a greater speed by applying a force to the object, you increase the kinetic energy, K, of the object. Similarly, if you decelerate the object to a lesser speed by applying a force, you decrease the kinetic energy of the object. We account for these changes in kinetic energy by saying that your force has transferred energy to the object from yourself, or from the object to yourself. In such a transfer of energy via a force, work, W, is said to be done on the object by the force. More formally, we define work as the following. Work, W, is energy transferred to or from an object by means of a force acting on the object. Energy transferred to the object is positive work, and energy transferred from the object is negative work. And the units of work are the same as the units of energy, joules. Don't get confused by the traditional meaning of the word work. In the physics definition, work is only done if there is a displacement involved. If you pushed on a wall all day until you're hot and sweaty, in the end, you've done no work because the wall hasn't moved. Let's develop an expression for work, and let's use a constant force to do that work. We know that a force causes acceleration, so let's let the x direction be the direction of the displacement, and we know from using equations of motion that we work separately in the x and the y directions. So an acceleration in the x is caused by a force in the x. Even if the force has a component in the y, that does no acceleration in the x. Okay, so if we're using a constant force, that means we can use our equations of motion because we have constant acceleration. And we'll use this equation. We'll solve this equation for acceleration. And we'll take what we get for solving for acceleration and plug it in for A in Newton's second law. We'll expand that and rearrange it. And we see that F times D is equal to 1/2 mv final squared minus 1/2 mv initial squared. You'll recognize these terms, 1/2 mv squared, as kinetic energy. So this term here is the final kinetic energy, and this term here is the initial kinetic energy. So the difference in those two is the change in kinetic energy. And we know that is work. And the work is achieved by applying a force over some distance. Let's look at an example. How much work is done on this 4 kilogram block as it moves through a certain distance? Well, the first thing we want to do is figure out what's the acceleration of the system, and to do that we need to draw a force diagram. So there we have it, the weight of the 4 kilogram block, the normal force on the 4 kilogram block, and the tension in the string, and the weight of the 10 kilogram block is going to accelerate the system. So let's apply Newton's second law to figure out the acceleration. The sum of the forces in the x is equal to mass times acceleration in the x, and here we're going to let the tabletop be the x direction, and the pulley changes that direction of force so that we can say the 10 kilogram mass is also moving in the x direction. Here's my coordinate system here. So T, if I look at this whole thing as a single system, the tension in the string is an internal force. So one of them points in the positive direction, one of them points in the negative direction, so they cancel each other out, as we expect with internal forces. Then the weight of the 10 kilogram block is the only force now in the x direction because we have said up here that this surface is frictionless. And then that force is accelerating how much mass? Well, both blocks, m1 plus m2. So solving that equation for A, we see that the acceleration of this system is going to be 7 meters per second squared. Okay, now that we know that the acceleration is 7 meters per second squared, let's find out what the tension is in the string is. So to do that, we have to apply Newton's second law to either of the blocks individually so that tension is an external force. And I show here the solution for solving it using either block. If I use the first block, the tension is the force that accelerates 4 kilograms at 7 meters per second squared, and that tells me the tension is 28 newtons. Or I could have looked at this 10 kilogram block. It has 2 forces acting on it in the x direction. Its weight in the positive direction, the tension in the negative direction, and those sum of forces act to accelerate mass number 2, which is 10 kilograms at 7 meters per second squared. And so using block 2, I arrive at the same answer, that the tension is 28 newtons in the string. So, how much work is done on the 4 kilogram block as it moves through a distance of 3 meters? So, first I'm going to calculate how fast is it moving. So here's my calculations. I know it's a constant tension, so it's constant acceleration. I can use my equations of motion. The block starts from rest. Its acceleration is 7 meters per second squared, and the displacement is 3 meters. Solving for the velocity, I see that when it reaches this point, after moving 3 meters, it will be traveling at the square root of 42 meters per second. Now that we know how fast it's moving at this spot, we can calculate what is its change in kinetic energy from here to here. So our change in kinetic energy, delta KE, is the final kinetic energy minus the initial kinetic energy. We know it started here at rest, so this initial kinetic energy term is 0. And we saw that at this location, it is now moving at the square root of 42 meters per second. So I plug that in for velocity. The mass is 4. I work out the math, and I see that it is 84 joules difference now of kinetic energy. The block has gained 84 joules of kinetic energy. Positive work has been done on this block by the tension. Now let's see, does that agree with our new expression for work, that work is equal to force times distance? Well, the force pulling on the block is the tension in the string. It's 28 newtons, and the displacement was 3 meters, and 28 times 3 is 84. So yes, it does agree with our expression for work does agree with the old way we would have done it before we knew how to use this expression. This is how we would have had to calculate the change in kinetic energy. Now we have a simpler way of doing it. Force times distance. Notice also that units of force is newtons, units of distance is meters, so a newton meter is the same thing as a joule. Remember, work and energy have the same units, joules.
All right, so in the example that we just saw, the string pulling on the block was pulling in the horizontal direction, okay? It doesn't have to be that way. It could be pulling up. Remember the bucket of sand or the box of sand problem that we did? You pull it across the floor. Even though you're pulling slightly upward, the box is still moving horizontally. So we notice that this that this force F has X and Y components to it. The direction of the displacement of the box is in the X direction. The Y component of the force does no work. There is no displacement in the Y direction. Kind of like the example you saw of my son pushing on the wall. The physics definition of work says he didn't do any work because no matter how hard he pushed, the wall didn't move. So it's the same idea here. The Y component of the force, there's no motion, there's no displacement in the Y direction, so there is no work done by the y component of the force. Now they're not drawn in the picture, but in the y direction we know we also have the weight and the normal force, so the sum is 0 because it's not accelerating in the y direction. Okay, so only the x component of the force is doing the work, and we know that using this diagram and being consistent with what the book is using, they use the Greek letter phi instead of theta for the angle. That's fine. So cosine of phi times f is the x component of the force. So then the work is the x component of the force times the displacement. We can rewrite that, since fx is f cosine phi, that the work is fd cosine phi. This is, we give a name to this, it's called the dot product. Anytime you take two vectors and you take the components of one vector that's in the same direction as the other and you multiply them together, that is called the dot product. And that's what we're going to use to calculate work, and this is the way you write it, F dot D. Okay, what if the force was greater than 90 degrees? Okay, now my x component of force is in a direction that is opposite to the displacement. Notice that the block is still moving to the right, but my x component of force now is to the left. Remember what we said earlier in the year about acceleration and velocity? If they have the same sign, what is happening to the object? If acceleration and velocity have the same sign, it's speeding up, right? If velocity and acceleration have opposite signs, the object is slowing down. Well, we know that acceleration is always in the same direction as the force. So if my force is in the negative x direction, my acceleration is in the negative x direction, but my velocity is in the positive x direction. So in this example, the block will be slowing down. In my previous example, right, this block will be speeding up because my x component of force is in the same direction as the velocity, and so the object will speed up. This is an example of positive work. Positive work means the object is speeding up and there's more kinetic energy at the end than there was at the beginning. On the other hand, this is negative work. This object will be slowing down and it will have less kinetic energy at the end than it did at the beginning. Okay? And that will show up in the sign of the work. If the work is has a positive sign, we know it has sped up, and if the work has a negative sign, we know it has slowed down. Okay, let's look at our same example, but this time let's include friction. Okay? I didn't bother saying the coefficient of friction, and you have to figure it out. I just flat out tell you there's 5 newtons of kinetic friction. Okay? So if you redo the calculations, I don't show it here, before our acceleration was 7 meters per second squared. Now that we have kinetic friction here, as we expect, that friction is going to slow it down somewhat. And so when you do the calculations again, you see that we get something less than 7. We get 6.64 meters per second squared as our acceleration. And the tension in the string becomes slightly greater because the acceleration is less, so the tension in the string becomes greater. Now, if I ask the question, how much work is done on that 4 kilogram block, now I've got 2 forces acting in the x direction. Remember, the weight and the normal force, they're perpendicular to the direction of motion. They do no work. All right, so I've got work done by the tension force. That's going to be positive work because the force and the velocity are in the same direction. In other words, that force acts to increase the kinetic energy of the block, whereas the frictional force acts in the opposite direction to the motion, so that's negative work done by the frictional force, and we know that friction slows things down. So, what is the net work? What is the sum of all the work done on the block? Okay, so I'm going to look at the work done by the tension, and I'm going to look at the work done by the friction, and I'm going to add them up to get the net work. Just like the net force is the sum of all the forces, the net work is the sum of all the work done by all the forces. Okay, so WT will be the work done by the tension, and The tension's 31.6, the displacement is 3 meters, so that gives me a positive 94.8 joules of work done by the tension force. How much work is done by the frictional force? Well, the frictional force is in the negative direction, 5, and its displacement is 3, so that gives me negative 15 joules of work is done by the frictional force. So when I add those up, I get 79.8 joules is my net work. The total work done on the block by all the forces in the x direction is 79.8 joules. And if I wanted to use that to calculate the velocity of the block as it reaches this location, now I can say kinetic energy, if it had 0 here and the delta is 79.8, then I have 79.8 here. So I take that 79.8 and I set it equal to 1/2 mv squared, and I know the mass of the block. I solve for the final velocity, and I can figure out how fast it's going here, 6.32 meters per second. So now you see we've got a different way of coming up with the final velocity. If you did this problem last week, you would have had to find the acceleration and use equations of motion to find out how fast it's going. Now we have another way of doing it, and as we go through the year, you'll find out this way oftentimes is a faster approach, okay? With experience, you'll see that, okay? Let me point out, over here, if I write these equations algebraically, there we go, okay? If I write these equations algebraically, the work done by the tension is tension times distance, and the work done by the friction is friction times the distance with the negative sign. You'll notice that I can factor out the d in that equation. So if I factor out the d, I get this, and you'll recognize T minus Fk as the net force. So I can rewrite the equation as the net force times the displacement equals the net work. So in other words, you can either look at it as the net work is the sum of all the works done, or you can look at it as the net work is the work done by the net force. Okay, so you can, it's up to you. So let's go over the main ideas, hopefully, that you picked up today. First of all, the definition of work. Work is the transfer of energy by means of a force, either transferring energy to an object or away from an object. And if you transfer the energy to the object, we call that positive work, and the end result is there is more kinetic energy in the object than there was before. On the flip side of that, negative work is taking energy away from the object, and the final kinetic energy is less than what it had to begin with. And when we calculate the work using this equation, for now, we have to say the force must be constant. Okay? We will be looking at examples later next week when the force is not constant, but for now, we're going to look at constant forces, and the work done by a constant force is just the force times the displacement. Remember that forces perpendicular to the displacement do no work. If you plug it into the equation, FD cosine phi, to be perpendicular means phi is either 90 or 270. And the cosine of 90 is 0, the cosine of 270 is 0, so we get 0 for our answer in our equation for amount of work done by forces in those directions. We calculate the work done by the force with the dot product, which means we take the component of the force that is in the direction of the displacement and we multiply those two together. Remember that the work units and the kinetic energy units are the same. Since work is a measure of how much the kinetic energy has changed, then that makes sense that the work units is the same as the kinetic energy units, joules. And remember that net work, we can either sum up all the works done by each force and add those together to get our net work, or we can first find the net force and then multiply that by the displacement, and that gives us our net work. Okay?
Seen at 4,000 frames per second, the slap seems to dislodge the brainiac's face. When the cheek is struck, a shockwave travels through the skin's collagen, arriving at the opposite cheek almost instantaneously. Then the skin vibrates as the elastic fibers wobble under the force of the blow. All this in 1/10 of a second.